Hey, this is a screencast. I'm calling Confidence in Differences of Means, Normal Case. So we're going to talk about the difference of two means and the role confidence intervals can play when we're talking about the differences of two means. And this comes up when we're talking about comparing populations. Comparing two populations. And what we might talk about when we're comparing two populations is what to expect of the differences of some measurement between the two populations. You can think of maybe we're running an experiment and we've got a control group and a experimental group, and we're measuring each to see the effect of some treatment, and we want to compare the average effects of the treatment against the measurement on the control group. That's a simple example of wanting to compare two measurements between two groups. So I'm going to present the way this works in a specific context. So in this screencast, my two groups are going to be college athletes. So those are my two groups. Women who play college lacrosse and women who play college soccer. The measurement I'm interested in comparing these two groups with respect to is their height. The data I'm using will be from the NCAA. So let's let x be the random variable that gives the heights of the women lacrosse players. And then it'll be in centimeters. And let's let y be the random variable of heights of women's soccer players. Also in centimeters. So a natural question is to ask, do we expect one group to be taller than the others? And of course, we're asking on average. And when we ask that, we're asking, do we expect the lacrosse players to be taller on average than the soccer players? Do we expect the soccer players to be taller on average than the lacrosse players? Or do we expect them to have the same height on average? I mean, these are three natural questions to ask. These are questions about the expected value of each of the random variables. And we can phrase these as questions about the difference in these expected values. So the first one here could be, is this difference positive? Or it could be, is this difference negative? Or is this difference equal to 0? There's a whole theory of random variables and algebra of random variables. And we've talked about those a little bit. We've talked about what happens to these descriptive statistics of a random variable if we take the random variable and multiply it by a constant or add a constant to the random variable. You won't be surprised to learn that if x and y are random variables, then x minus y is also a random variable. And you wouldn't be surprised to learn that the mean, or the expected value, of this new random variable is the difference of the expected values. So we're going to take these as fact. Also, you won't be surprised to learn that if x is distributed normally with mean mu x and variance mu x squared, And if y is distributed normally with mean mu y and variance sigma y squared, then the difference of these two random variables is also going to be normal. And its mean is going to be as described, and its variance is the sum of the variances. This latter one might come or might not be obvious to you, but we've talked about something like this in the past. You can go back and look to see where we talked about the linear combination of random variables. After all, this is a linear combination of two variables. But we're going to take this as fact going forward, and we're going to use this to calculate the confidence intervals for this difference of sample means, using the ideas that we've developed so far. It's going to be a straightforward application. But in a new context, it's really pretty neat. One other thing that I want you to recall is that if a random variable is distributed normally with some mean and variance, then its associated sample mean is also distributed normally with the same mean, and its variance is given by that expression. Now, we're used to writing this second argument in this notation using standard deviation. The book uses variance. So for us, if we were using standard deviation, we would write it that way. And that's the way I've done it in screencasts up to this point, but today I'm switching to use variance in this second argument for a normal distribution. So pardon me for any confusion that's causing. So with this information in hand, this idea that x minus y is also a random variable, and that if x and y are normally distributed, which we'll assume they are, you'll see, then x minus y is normally distributed with the norm as given, or the expected value is given, and the variance is given. So let's apply this to our example with women college athletes and their heights. So here are the measurements we have for heights of women who play college lacrosse and women who play college soccer. It's worth pointing out that these data sets are small, but that isn't going to be a problem because we're starting out with the assumption that they come from a normal distribution. Let's just count up our data set. So how many data points do we have here? Well, 4 by 3, so we've got 12. So I'm going to say here the number of measurements of women who play lacrosse, which goes with our random variable x, that's 12. And this other data set here, the number of women who play college soccer, that looks like we've got 8, 16, 15. So those are the size of our data sets. We can now throw this data into R and do these calculations. So according to R, the sample mean for the heights of our lacrosse players is 167.2417 centimeters, and the sample standard deviation is 4.82973. Same thing for the sample mean of heights for the women who play college soccer is 163.7133, and the sample standard deviation is 7.803467. And again, these are all in centimeters. Now, somebody who doesn't know any better would look and say, oh, look, these means are different. And that's a pretty big difference. So, of course, here it looks like the lacrosse players are taller than the soccer players, and then they might stop there. But we know that there's variation, and we know that these differences here are pretty significant. These standard deviations are pretty significant, and we want to be careful. And we're going to do this analysis and find a confidence interval to tell us what is the interval that we expect the differences in the expected heights to be. And right off, we have to calculate the difference in the means. And so x bar minus y bar is 3.528333. And that's not 0. We acknowledge that that's not 0. But again, we point to these relatively large standard deviations that might tell us that maybe our expected difference could be 0, could be close to 0. So let's calculate the 90% confidence interval. For the expected value of the difference, which we know is this, to see if it contains 0. And if it does contain 0, then maybe we expect these players to have on average the same height, or it's possible. All right, to start this calculation, first we need to know what the alpha level is, and to do that, right, we set 100 times 1 minus alpha equal to our 90%, and we've done this before. Alpha is 0.1. And so alpha over 2 is 0.05. Now, since x and y are normal, this tells us x bar and y bar are normal. And so x bar minus y bar is normal. Moreover, we can use what we talked about before to say x bar minus y bar is distributed normally with mean mu x bar minus mu y bar, and standard deviation, or variance in this case, right? We're doing variance. Variance is the sum of the variances of x and y. Well, x bar and y bar, right? Because we're talking the sample mean distributions, not the original distributions, the sample mean distributions. So that's why. Well, yeah, okay, so we're good there. But let's look at this for a second. I'll do this in blue. The sample, or the standard deviation of the sample mean is the standard deviation of the original distribution divided by the square root of the sample size of those values. So that means the variance of the sample mean is the square. So we square the standard deviation of our original distribution, and we square the square root, and so we end up just with nx. So this can go in here. So I'll rewrite that. X bar minus y bar. The difference of the sample means is normally distributed with mean mu x bar minus mu y bar. And here, the standard deviation, or the variance rather, is mu x squared over nx plus mu y squared over ny. And because our populations were normal, we're going to replace these with the sample standard deviations. And so this is going to tell us the standard deviation of x bar minus y bar is the square root of the sum of the variances. And that's what we're going to use to calculate our confidence interval. So the confidence interval, its endpoints look like the expected value of the difference plus or minus this z-score, this z percentile, related to our alpha level, times the standard deviation. So our expected value here is this expected value, which will use our sample means, or difference of sample means. So we got that. The z percentile for that alpha level, we know how to do that. And the standard deviation, that's this right here. So let's go and calculate these. X bar minus y bar, we did that already. I'm just recopying. The z percentile for our alpha over 2, that's the simple R command for the alpha over 2, and then we put in the parameters to go with the standard normal. You know, I'm not sure. You might be able to just drop those and do Q norm of 0.05, and R will assume that you're using the standard normal. That might be an interesting thing for you to check. But here we get negative 1.644854. And then now let's calculate the standard deviation. So the standard deviation of our difference, because, right, I'm calculating this because it's this. It's the standard deviation of this new random variable we're talking about. The standard deviation is the square root of our sample standard deviation for the x's squared divided by that sample size. Then we add the sample standard deviation for the y's and divide by the y sample size. Throw this into R or your favorite calculator, which should be R by the way, and you get 2.450197. All right. Take these suckers, put them in this formula, right? Calculate x bar minus y bar, our expected value, our sample expected value, and then our times our z percentile times our standard deviation, and we get, all right, 3.52833 plus or minus negative 1.644 and some digits times 2.450 times some digits. I'm just dropping them now because I don't have space on my page. And you do the plus and minus, and you'll get, let me get rid of this equal sign. You get the left endpoint is minus 0.50188815, and the right endpoint is 7.558548. All right, I kind of didn't use my space very well. Let's go to where I have more space here. So this tells me the 90% confidence interval for the, let's call it the mean difference of population heights is negative 0.50188815, comma 7.558548. Right? That's the 90% confidence interval. Or if I want to round, it's negative 0.5 to 7.56. This interval does contain 0, so it's possible to say that the true expected values of the difference of heights could be 0. But you see that's kind of on toward the left edge of the interval, and a lot of that interval lies above 0. So a reasonable person could say that we expect, what was it, the lacrosse players to be slightly taller than soccer players. But if you just look at this data, all you can say is the 90% confidence interval for the difference of means is this. Okay. So another way to say this is we conclude that the 90% confidence interval is 3.53 plus or minus 4.03 centimeters. That's the confidence interval for the difference in means. The difference in lacrosse players compared with soccer players. So the lacrosse players are slightly taller on average than the soccer players, but there's a larger standard deviation. Now, if you want to play around a little bit, you could ask, what's the 80% confidence interval? And with all the work we've done, it's pretty easy to come up with the 80% confidence interval. So let's just go back. We have all these calculations. And the only calculation that has to change is this. Because our confidence level changed, our alpha changes. So we just have to change this number. And I believe we changed it to a 0.1. It'll give us a different number here that we plug in here. So if you go through the calculations, these endpoints are going to change accordingly. So how do I want to write this? This increases alpha to alpha equals 0.2. So the new interval, or so not the new, let's say the 80% confidence interval is, well, do the calculation, you'll see it's 0.39 to 6.67. Or that is to say, or it's 3.53 plus or minus, oh boy, I didn't do this. 3.14 centimeters. And now you can see the left endpoint is above 0. So we can say with 80% confidence that we expect a soccer player to be taller than a lacrosse player. Okay, that's it. Thanks for watching. Hope this was helpful. See you in the next one.